Okay, here we go. So this is the first analysis video, and it's the first in the series for analysis that I'm making. And to give a brief overview of this series of videos, it'll kind of split into three main topics. Other people might choose a different grouping of topics or even different topics entirely, but I want to make this accessible while also getting into some deeper topics. So topic one is, I'm going to call it structure of the real numbers. Okay, and this will have several subtopics. First, we'll actually construct the real numbers. And I'll call it the real field. And we'll construct this from the rational field. And then we'll investigate some of its properties. And then we'll look at the topology of the reals and the Euclidean n-space. And then we'll look at sequences of real numbers and vectors in Rn. And in particular, we'll answer questions like, what does it mean for a sequence to converge to a number? And we'll investigate like how sequences can like help us elucidate the properties of the real numbers and other spaces. The second topic is, I'm going to call it calculus done right. And the done right part is in reference to the linear algebra book by Sheldon Axler, of course. And we'll study the familiar operations of calculus, but we'll do it in a greater depth. So we'll look at limits and continuity. We'll look at differentiability. We'll look at least Riemann integrability. We'll look at sequences and series of functions. We will look at the inverse and implicit function theorems. Okay, and we might look at a couple of other things, but that's a general overview of the topics we'll look at. And we'll cover them in a different way than you learn in calculus. The third topic, I'm going to call it abstract spaces. And you might say, well, what the hell does that mean? Well, so basically we're going to take a lot of the notions that we learn in the first two topics and think about how they can be generalized to a much more abstract setting. And you might say, well, that sounds really weird. But we will think about, like, what does it mean for there to be like an open set? Or what does it mean for a sequence to converge? What does it mean for a function to be continuous? And then we will generalize these concepts, and we'll generalize other concepts as well, and apply them to solve some really powerful or some really important problems using powerful techniques. So the first thing we'll look at probably is general metric spaces. We will look at vector spaces, at least briefly. There shouldn't be too many people watching this far into the series that make it to that point without knowing what a vector space is, but it's good to review it at least a little bit. We'll look at normed and Banach spaces. And then we will look at inner product and Hilbert spaces. And if you have studied quantum mechanics, yes, it's that Hilbert. Okay, it's the same Hilbert space concept, except now it's rigorous. And we might do more than this. So maybe measure theory, Lebesgue integration, Fourier analysis, differential equations, etc. But for now, let's just start at the beginning of topic 1, construction of the real field. And why do we need to construct the real numbers? I think it's a fair question. Like, well, what is a real number? We will answer that. And we won't go as fundamental as we could, but let's at least do this for motivational purposes. Let's remember the natural numbers, which is probably the most simple set of numbers that you can remember learning about. We denote this by bold-faced n. 1, 2, 3, 4, 5, etc. And these are the natural numbers. Okay, and what can we do with natural numbers? Well, we can count things. We can call these the counting numbers. And if you want a rigorous definition of them, you can look at the Peano axioms. If you haven't heard of these, I would definitely stop at this point and look them up and study them a bit, especially the principle of mathematical induction. But this isn't our purpose here. And what can we do with natural numbers? Well, we can do a few things. So each natural number has a successor. And it's unique. So each natural number has a unique successor, which we will denote n++. And this borrows from C-based programming languages. I think Terence Tao also uses this in his book, which I think is kind of cool. So for instance, to give an idea of what I mean, well, 1 is 2. 2 is the successor of 1. And 2 is 3. And by that we really mean the successor of the successor of 1. Is 3. Okay, so that should make sense. This isn't anything too revolutionary. And one important thing to note, though, we can actually define addition in terms of this succession. So, given natural numbers n and m, n plus m, well, that is, well, we take n and we find its successor, and then we find that number's successor. Then we repeat this. How many times? Well, we repeat it m times. And it's the mth. successor of n. And, we're not doing this super rigorously. This is just kind of giving you an idea at a high level of where this comes from. Think of this video as very much motivational. We're not doing heavy-duty math yet. And we can define... So we've defined addition in terms of succession. And what we can do, we can define multiplication in terms of addition, which is the familiar way to think about it. And how many times did we add? M times, right? Okay. Now, so the natural numbers have some nice properties, as we've laid out. However, they also have some serious deficiencies that we haven't talked about. So we can frame problems in the language of the natural numbers that don't have a solution in the natural numbers, even though we would like them to. So for example, here's a question. Does there exist a natural number x with, I don't know, how about x plus 4 equals 2? Okay, does that exist? And remember, natural numbers are just these numbers 1, 2, 3, 4, 5, etc. And in fact, no, this doesn't have a solution in natural numbers. So what we are compelled to do, because we can, again, frame these frame these problems in the language of the natural numbers that have no natural number solution, we are forced to kind of expand our notion of number to this new set. And we call this set the integers. And we denote it with this bold-faced z. Thank the Germans for that. Okay. And what have we done? Well, we've added in a lot of new elements. In particular, we have an additive identity. Zero. And this element is special because for all integers n plus 0 equals 0 plus n equals n. Okay? And, that's interesting enough. We didn't have that before, but we actually have added something else that's really important, and this is called additive inverses. To each integer n, we associate this unique additive inverse. We denote it minus n. And it has the property that n plus minus n equals minus n plus n equals 0. So if you add a number to its inverse, you get the identity. Okay? And so that's pretty interesting. And let's think, can we now answer questions like the one from above? In Z. And the answer is yes. So, we're not proving all these properties in depth, otherwise we would be here for much longer. But, take x equals minus 2. Then minus 2 plus 4 equals 2. And x equals minus 2 satisfies the above equation. Okay, so we fixed this problem that we had in n. Now, so that's great. However, we run into similar problems in Z because we can formulate problems using the language of Z that have no solution in Z. And let me give you a perfect example. Does there exist an integer x such that 2x equals 3? Think about that for a second. The answer is no, of course. You know, there's no way that you can double any integer and get 3. It's just not going to happen. Okay, so what we do, again, we graduate from the set of integers to a new set called the set of rational numbers. And, you know, we haven't defined what this m over n thing means, but we think of these as fractions. And again, like if you want to construct the rational numbers, you can do that in like a course, I believe on like ring theory. Yeah, I believe you would do that in a course on ring theory, certainly in an abstract algebra class. And, you know, just as a refresher, we define operations on Q in terms of those from Z. So to add m over n plus p over q, we find a common denominator. And then we compute. Okay, and then, so this is addition, and then multiplication. Well, this is actually easier because we just multiply the numerator, then we multiply the denominator. Okay, and I guess we kind of cheekily used the multiplication in the definition of the addition, but bear with me. Okay, now Q has a lot of nice properties, and in the next video, I guess we will actually explicitly outline these properties. However, let's think about what's wrong with Q, because we're going to be downers today. And what's wrong with Q? Well, like, you can solve all sorts of problems, like this equation 2x equals 3. Well, we divide both sides by 2. And we get, of course, x equals 3/2. Okay, cool. So we can solve a lot of equations like this, and like you're really familiar with doing this if you ever studied algebra, of course. But the problem is we can actually formulate problems in Q that have no solution in Q. And here's a question. Does there exist a rational number p with p squared equals 2? Okay, and you know, right now, the answer to this problem shouldn't be too surprising to us because we're living in 2023. But keep in mind, this is the sort of question that actually gave the ancient Greeks a lot of trouble. And you'll soon see why, but let me give you the reason. So, we all know Pythagorean theorem, of course. And the Greeks were big on geometry. Now, the Pythagorean theorem says that if we have this right triangle with side lengths, as I've labeled here, then we have this famous relation a squared plus b squared equals c squared. Okay? And this relationship governs the lengths of the legs. And this is a leg. This is a leg. And what's this part? This part's called the hypotenuse, of course. Okay. So it seems really natural to ask, is every triangle valid if our only numbers are rational numbers? So what if we have a triangle whose legs are both of length 1? Okay, this seems like a very reasonable thing to do, right? Like you've measured out a length of 1 with your ruler, and you've done that twice, and you've drawn these things at 90 degrees to each other, and we draw a hypotenuse, right? Okay, so this seems like it exists geometrically, and what should this length of this hypotenuse be? Well, by Pythagorean theorem, c squared equals a squared plus b squared. And in this case, that's 1 squared plus 1 squared, which is 2. So c should be root 2. Okay, so far so good, yeah? Okay, but here's the kicker. I'm going to call this lemma 1. This is our first time proving anything. There is no rational number p with p squared equals 2. Okay, so from here on, I'm going to write quotation marks around root 2. Well, I hope you don't hear my neighbor's dog barking. Okay. And let's go ahead and prove this. This proof is due, I believe, to Euclid. Again, one of the Greeks. So let's actually suppose, for the sake of contradiction, that there is a rational p. With p squared equals 2. And let's write p equals m over n. P is a rational number, so we should be able to do this. With m and n having no non-trivial common divisors. And by that, we really just mean that this fraction is written in lowest form. And the point of that is, if it wasn't written in lowest terms, say we had 6 over 4, we could reduce that to 3 halves and nothing would change. So this should be something we can do. Okay. Well, this all seems good so far. Then, well, p squared equals 2. So let's substitute for p, m over n. And then this squared, so we get m squared over n squared equals 2. And multiply through by n squared. M squared equals 2n squared. Okay, and we have something interesting here because, so m squared equals 2n squared. Well, n is an integer, so n squared is also an integer. But then we're multiplying it by 2. And if you multiply any integer by 2, you get an even integer. So this shows that m squared is even. Okay, but m is also an integer, and if you square any even integer, or sorry, this proves that m is even. Oh my gosh. Because if m wasn't even, well then m would be odd, and then m squared would be odd. Okay? So, since m is even, we can write m equals 2t for some integer t. Okay, and now let's go back to this above line where we had m squared equals 2n squared. Well, let's substitute m equals 2t. And then let's divide through by 2. And hold up, we can use the exact same reasoning that we used above to see that n squared is even. But this also forces n to be even. But this is a contradiction. M and n have a common divisor of 2. Which actually contradicts our original assumption. Okay, so we've shown that there is no square root of 2. So, what do we make of this? I mean, if we take out a calculator, like, we can punch in root 2 equals 1.414, etc., right? You can do that. But since we haven't actually defined what it means to be a square root of 2, what exactly does this string of numbers even mean? It has something to do with approximation, you might think, and it does. But in this series, we'll actually answer questions like this in a more precise way. And starting next time, we will further understand these flaws and these holes in the rational numbers. But for now, like a really crude way to think of this is that, we think of Q as a number line where root 2 should be. There's just a hole. And it turns out there's actually many holes. In fact, there are far more holes than there are rational numbers in a real sense. And what we will do as we go from Q to R, we'll actually fill in all of these holes in a very rigorous way. And that's how you go from Q to R. And that's why we're not doing this now, because you can imagine it might be a tricky, precise process that involves us answering a lot of questions. So we have a lot of precise work ahead of us. In the next video, we'll look at Q as an ordered field. Okay, thank you. That's the end.